Okay, draw out these structures. So we're gonna need 6 carbons for this one, and it's gonna have 2 alcohol groups on it. So 2, 3, 4, 5, 6, and that, and an OH, and an OH. And remember the little oddity with this one that you leave the E in, the hexane, anytime you use a prefix in front of the suffix, which sounds kind of weird, but. Alright, so let's see, we've got 1 bromocyclopropanol. Alright, so I've got, are we okay with that being cyclopropane? And then, doesn't matter which one you pick as the alcohol group, being number 1, and then there's also a bromine coming off that same one. Since there's only 1 alcohol group, that must be coming off number 1. And so then I just need to identify that the bromine is also coming off that one. O-nitrophenol. Alrighty. So. And O is what? 1 away, 2 away, 3 away. Next to it? 2 next to it. Okay. Alrighty. And let's see, pentanol. 2, 3, 4, 5. And I have a, let's say an OH there. And a methyl group there. And a bromo there. Looks good. Make sure you have that little hitch down for the alcohol group. You can't put the alcohol group here. Why? Yeah, it looks like it's only 4 carbons. So make sure there's a corner there for the end. So I got a pentanol. So 2, 3, 4, 5. Well, 1 pentanol. All right. So there's another OH there, and then a BR and a CL and an F and an I. It's kind of silly, but there you go. And 1,2-ethane diol. Probably easier to just do it this way. Does it matter where those alcohol groups go? Top, bottom, left, right? It does not. Why? Single bond, so there's free rotation around that bond there, so it really doesn't matter where you put it. All right. So we got a cis-1 methoxyhexene. All right, that sounds good. Okay, so I'm going to put a double bond and carbon, and I've got a cis methoxyhexene. Okay. So what's going to be cis?
Is that like an O with the in place of the carbon? So it's like an event kind of thing. I don't know. I had a hard time with this one.
Sure, but what's cis in this case? What atoms are cis to each other? No, because that would mean that there'd be methoxys on both sides. Am I okay with that?
Oh, that's right, sis. Oh, I remember now. Friends are functioning yesterday.
So right now, I've got a double bond, and I've got a couple of things cis to it, right? I've got 2 of my 6 carbons, so I will put another carbon there. And I'll put another carbon there. 1, 2, 3, 4, 5, 6. So
Okay.
there are 6 carbons. There's a double bond there. And what else do I need? Oh no, those groups are cis to each other. Pretty nice. So methoxy. So Are we good with that?
Looks pretty.
You're not okay with that?
No, I said it looks pretty.
She doesn't look super happy with this one.
This was a hard one. This is a hard one for, yeah, everything's hard for me.
How do you know that the methyl group is off of the oxygen?
It says methoxy.
Well, like, how do you know that there's not a double bond to the oxygen on the first carbon?
Because methoxy means something specific. And what does that mean? What does methoxy mean?
There's one.
That there's one carbon added oxygen.
Okay, so what do we call that functional group? It's an ether. When you see methoxy, that means ether. And an ether couldn't be double bonded to any carbon because it can only have 2 bonds. So if it was double bonded to one carbon, it can't have a carbon on the other side of it. There's lots of ways you could do this. Usually, I mean, we could just throw out a 2, 3, 4, 5, 6, right? And then on this guy could be carbon number 1, and there's my OCH3. And then 1, 2, carbon number 3, there's a double bond. But now I got to go rearrange everything, don't I? So, okay, great. But then I'm going to have to, erase that, and then my whole thing disappears. So when I'm doing something that's complicated that's got a double bond in it, I just write the double bond down first. And then do the cis or trans associated with it, and then add carbons to it until I get to 6. It's, why is this guy named for the double bond instead of for the ether? How do organic molecules get named?
Longest chain.
Longest chain, that what? Why? Why the double bond? It's the most reactive, right? The first thing that's going to react on this is the cis double bond. So the ether is reactive, but not as reactive as the double bond. So that's why I'm going to name it for that instead of for the straight up for the ether. Anything else with this one? Propane triol. All right, so triangle. Something like that. Mm-hmm. Well, you got to be careful with this one.
How the double bond is? Or the OH?
Which end do you start from, the OH and double bond?
Start
Okay.
from the double bond.
Why?
That's what you're supposed to do.
Because it's more important, because it's more reactive.
Yeah, it's
Yeah,
more reactive.
it's more reactive, yeah.
Yeah, that's the answer. If somebody else asks you that, you can't say because Rob
Okay.
told me to. It's not going to work.
Because Rob told me to.
That only works when you're talking to me. That doesn't work when you're talking to anybody else.
Dang it.
So because the alcohol is not as reactive as the double bond, we're going to name this thing on the left-hand side for the double bond. So it'll be 1, 2, 3, 4, 5, 6. So it'll be a heptene. It'll be a 1-heptene. So 1-heptene. And what's attached to my heptene? A dimethyl, and they are both on carbon number 5. So a 5, 5 dimethyl, and what? A 6 hydroxyl. Okay. You. just the meth. Yeah. It's dumb, but so's grammar. Why would this be problematic? Doing it like this.
Because you can't see where the hydroxyl ends up.
Very good. So this looks good. It's telling you that there's a double bond there, and it's telling you that there's an alcohol. But then how do I designate in front of this where the double bond is and where the alcohol is? Right. So that's why it's not done that way.
Do you have to say sister trans?
Can somebody say why not? Carbon number 1 has what on it? 3 or 2 hydrogens, right? So remember what cis and trans is about. You pick one side and flip their positions. Did anything change? So if there's a hydrogen here and a hydrogen here, and then I flip-flop them, did anything change? Still an H on top and an H on the bottom. If there was a chlorine here and an H here, then I would have to call this what? Cis,
Just,
because there's an H right there. So there's definitely an H at this position. Are you okay with that? So since this is showing an H and an H, so is it cis to that? Sure. And it's also trans to it. So it's not cis or trans to anything, because there isn't anything for it to be cis or trans to.
So cis and trans is just referring to things that are connected to the double or the triple bond?
Just the double.
Just the double?
You can't have a cis or trans situation with a triple bond,
Because it's.
because there's only one thing on each side. Yeah. There's no geometric space to be offset from. Why are dehydration reactions such an important, and think about that, why this happens. So in a dehydration reaction, we're going to get a water molecule, right? Because we get a water molecule, nature seems to really enjoy making water molecules. And so these reactions tend to be very free energy intensive. So what do I mean by that?
You don't have to put energy in it to make it happen.
So what kind of reactions are they then?
Combination.
Spontaneous. These reactions that make water usually end up being spontaneous. So they're really important because you don't have to put a lot of energy into them to get them to happen. You just need to get it going, and then once it gets going, they usually can support themselves. And they're really, the other reason that they're really important is, what's the starting product? An alcohol, a very inexpensive OH, like an ethanol or something of that nature. When people are talking about building chemical plants, most of the time, there's some sort of eth and something. They're going to do an eth something or other plant. Could be an ethylene, which is double bonds, ethanol, alcohol. But the eth is important because it's really easy for nature to make 2 carbon chains with functional groups on them. So once you get the 2 carbon chain with a functional group on it, then I can start attaching stuff. If I've got something here and it's reactive, I can put it onto something else that's also reactive, and I can just keep making connections. So really, it's because it's cheap, because the fact that the reaction's spontaneous, and it's easy for nature to make those things. So what do we get here if I oxidize a secondary alcohol?
yeah.
We good with that? Can I keep going?
No, because it doesn't, it'd be non-reactive.
I can't react the ketone, right? That ketone is like, I'm done. I'm done being able to be oxidized at this point. You can oxidize this. What oxidizing agent do you need?
Oh,
So you can do what to it? You can burn it. But you're not going to find those things happening inside of a living organism. How about alcohols mixing with water? Do they?
yes, no?
It depends
Depends.
how long the chain.
Yeah.
Oh, that's right, that's okay.
That's carbohydrate. How come the carbohydrates are soluble in water? Every single one of those carbons that's hydrophobic, not water-loving, has an OH group on it that is water-loving. So the carbohydrates are very easily solubilized. Okay. Any questions with this? Good.